So hello everybody, thank you Bastian for the introduction and thank you for inviting me to give this webinar today. My name is Katie Facer-Childs and I work at the UK Centre for Ecology and Hydrology. I've been there for about 10 years now, working primarily on seasonal hydrological models and seasonal hydrological forecasting. And I've recently taken over from my group leader, Jamie Hannaford, as the lead of the UK Hydrological Outlook. So I could talk about lots of other forecasting systems today, but I'm going to focus on the UK Hydrological Outlook because that's where most of my expertise lie, and I can tell you that in lots of detail. So before I begin, I wanted to just share that these are some of the 30 odd people who have been involved in the Hydrological Outlook over the past 10 years or so. And yeah, you can see it's a very wonderfully diverse group of people, and so really proud to be a part of this group and thanking all of them for all of their research. I will also be talking about some other research from other members of UKCEH as well later in my presentation who aren't on this list, but yeah, this is the main list of people that have been working in the Outlook for the past 10 years. So what I did was I've created this kind of transport route map that has a look at the past 10 years of the Outlook, and it shows us lots of different branch lines. So we have a couple of different colors. So for example, the green line shows, the green and the red and the blue lines show some of our methodologies for forecasting. The yellow line shows the Met Office input. The black line shows different dissemination methods we have in the Outlook. The navy blue line shows the National Hydrological Monitoring Programme and Hydrological Summary. The orange line is Cosmos, our soil moisture network, and then the purple line is on research. And this map kind of shows you how these things have interacted over the past 10 years with some of these stations, highlighting some of our key papers and outputs along the way. There's also a list of our collaborators here along the bottom. So it's not just us that run this Outlook. We're in partnership with the British Geological Survey, the Met Office, and the measuring authorities for the four parts of the UK as well. So just to talk you through what I will talk about today, I'll have a bit of a mention about why we do seasonal forecasts and how the Outlook began. I'll talk to you about the different methods we use of doing seasonal forecasting before going into some of the advances in these methods that we've been working on in the past few years. I wanted to talk to you as well about user engagement and forecast communication, which is a really critical element of our outlets, and then go into some of the international developments that we've been working on too. So why do we do seasonal forecasting? I should probably say, what is seasonal forecasting? Flood forecasts tend to be quite short lead time, so running up to about a few days to a few weeks, and then seasonal forecasting picks up the interim, so after that. So it tends to start at a maximum of 2 weeks, but generally starting about a 1 month lead time. So we're looking at what's going on over the next month, but also then what's going on over the next season. So it's kind of a 1 to 3 month outlook, but it also can push out to 6 months and even a year in some situations. And this is really important for lots of decision makers. Why? You can understand that people really want to know when a flood event's likely to hit and want to be alerted to flood risk. But seasonal forecasting is much more focused on drought events, but also on flood-rich periods. So not only is it important to know when a specific flood event might happen, it's also really important to understand when a season might be flood-rich. So there might be multiple flood events happening over the coming few months. And that really helps with disaster risk reduction and preparedness for extreme events. Obviously, industry uses a lot of water, so manufacturing have high water needs, and they would like to know some of the more long-term forecasting systems as well, and what's going on over the longer term. For public water supply, they'd like to know information about what is the risk of hitting some critical management thresholds. So are they likely to hit the thresholds of which they need to implement temporary use bans or start doing water transfers across different parts of the country, for example? Obviously, the environment is very affected by drought in particular, but also flood-rich periods and extended periods of extreme conditions. Agriculture, similarly, knowing what's going on over the next few weeks and months really helps agricultural decisions, and pushing forecasting out to several months and even a year can really help them with their management decisions. And then less importantly in the UK, but definitely in other parts of Europe, There's lots of requirement for hydropower, estimations of how much water is likely to be in reservoirs and how much hydropower they're then likely to be able to generate from that. So how did the outlook kick off? So in the years 2010 to 2012, we had a significant multi-annual drought event in the UK. We had 2 really dry winters, and that led to some really significant drought conditions in the summer of 2012. And the media and the government were all picking up on questions asking, well, what's the likelihood of us having a 3rd dry winter, a really unprecedented long drought event that was going to go on for 3 years. So yeah, the media were really picking up on hosepipe bans being likely, potential standpipes could come in again if there was likely to be a 3rd dry winter, and a real severe threat of extreme drought. So the government came to UKCEH and asked us, well, what is the likelihood of there being a 3rd dry winter? So we went away and we did some analyses and set up some different methods to be able to have a look at that. And that was the foundation of the Hydrological Outlook, really. Now, unfortunately, what happened was a really seriously transformational event. I should say, well, fortunately or unfortunately, it was the end of the drought event, but that kicked us straight into a really significant flood event that hit the UK. And you may remember this graphic if you are a UK-based participant. This graphic of block of flats in Newcastle got so undermined by water that they really nearly collapsed. And yeah, this news article just says that there was only 1.8 inches of rain needed by the end of the year for it to be the wettest ever in the UK, which, considering up till the end of summer, it was in significant drought conditions. That's only a few months of such wet weather that it could have totaled the wettest in the whole record. So these are just some time series data. The top graph here, you can see this is the River Thames at Kingston. And this just shows you the flow time series up to the summer of 2012. Was really, really low for that preceding 2 years, and then it jumped up really, really high and went into some really wet conditions. Similarly, with the standardized stream flow index plot, you can see a jump from significantly dry, extremely dry weather up to really, really wet very suddenly in that time series. So I'm going to talk to you now about the principal forecasting methods that we use in the Outlook. There are 3 main methods that we use, and I'll run through these in turn. Climatology is not one of our methods, but I wanted to just go over what climatology is because I'll mention it a couple of times. It's used as our benchmark of how good our forecasting is against climatology. So climatology is the most basic way you can perform a forecast. And all it does is it looks back at the historic record of river flow data and then has a look at what are the preceding values of river flow for that time of year in the historic record, and tots them all up, and you can use that to provide a probabilistic distribution of flow likelihood, or you can calculate a deterministic, just a simple average of what's the past has shown you if that's required. So that's just a basic summary of what's happened in the past. One of the methods that we use in the Hydrological Outlook is persistence and analogues. This was set up by Cecilia Svensson, and she published about this method in 2016. She produces we now produce, because she's retired, some maps and some different graphs about how these forecasts are produced. But the way that we do those is, so they're kind of 2 separate methods, but they're both based purely on the river flow data. So it's using historic river flow data. It doesn't use any hydrological models. It doesn't use any climate input data. It purely uses historic flow data. And then there's 2 methods that we use here to calculate a forecast. One of those is called persistence, and that simply persists the river flow anomaly from 1 month into the next. So if the river flow, for example, was 80% of average for June, we would have a look at the July forecast being 80% of the June average. And that's actually a really, really good forecasting system in a lot of situations, particularly in the south and east, where rivers are very persistent. They're quite slow moving. There's lots of groundwater dominance. You can get some really good forecasts that way. The second way is through the analogues, is hydrological analogues. So we use the historic river flow series again here. And what we do is we have a look at kind of the shape of the curve of the hydrological, the flow going up to today, and we look back in the past and we see, well, where have river flows had a similar pattern over the past few months, and then have a look at what happened in those analogous examples, what happened next. So we pick out generally 5 examples of where flows have followed a similar pattern to the recent past, and then we have a look at what's happened moving forwards. So those are persistence and analogues. Those are very simple statistical methods that use just the river flow data. The next example of the method that we use is called ensemble stream flow prediction. Now, this does use a hydrological model, but it doesn't use any climate forecast. And Sean Harrigan published about this method in 2018, benchmarking ensemble stream flow prediction skill in the UK with the GR4J model. And again, we produce lots of different plots for these outputs, likelihoods of falling into different categories, and some bar charts as well. And the way this method works is that actually, unlike a climatological forecast, we know where we are now. So we can kind of discount some of the examples of what's happened in the past. So what we do is we look at the historic rainfall and potential evapotranspiration data. And we look in the past to extract that historic data. So we're not using a climate forecast, but we are using historic observed climate data. So we look back in the past and we'll say, okay, if we want to run a forecast from July, we would have a look at all of the historic examples of rainfall and PET from July in the record. And what we do is we run a hydrological model. So we've actually upgraded now from GR4J to GR6J in our operational forecasts, and we will run that model using observational data up to today, and then we'll run that model using historic climate data forwards as our forecast. So we will run up to today, and then we'll pretend that the rainfall and the PET moving forward is the same as it was in 1958 or 1959 or 1960. And each year of historic data will provide an ensemble member of what could happen next if we saw the climate conditions that we have had in the past. And again, you can plot up a probability distribution from this, or you can get a deterministic output if you need to. The third method we use for our forecasts is another step up in complexity in 2 ways. We use a gridded hydrological model. So it's the GR6J model we use for ESP is just a lumped catchment model. But for the more complicated method, we use the grid-to-grid water balance model. But we also run that with climate forecasts from the Met Office. And this system has been published by Vicky Bell and her team in 2017, and it has been developed recently, and I'll talk to you about those developments very soon. But I want to just tell you how we did this originally for the majority of the past 10 years, because it's only been updated in the past year. So the way this works is, so previously, the previous Met Office input that we had was out of the Glossy 5 rainfall ensemble from the Met Office. Now, there wasn't much skill in those climate forecasts in terms of exactly where that rainfall is going to fall spatially across the UK. So what the Met Office would give us was a spatially uniform set of ensemble members as a percent of average. So they would say, okay, well, rainfall is likely to be 90% of average according to this ensemble member, or 30% of average according to this ensemble member. And what we would do is we would go away and we would then aggregate that distribution according to the historic pattern. So generally in the UK, rainfall hits us far more preferentially in the north and west due to the way our atmospheric circulation hits us in from the Atlantic, with far less rainfall falling into the southeast. So we would just distribute that uniform ensemble as a percent of average across the UK so that it's preferentially falling in the northwest. And what we do with that data is we run the observed rainfall and potential evapotranspiration through the gridded grid-to-grid model, and that gives us a really detailed, it's quite a complicated model, it gives us a really detailed estimate of the initial hydrological conditions. And then moving forwards for the forecast, we run a more simple water balance model, which is still gridded, but it's just more simplified to run those rainfall forecasts through the model. And that gives us our our ensemble forecast from the grid-to-grid water balance model. It's not just stream flow that we forecast, we also forecast groundwater information as well. So this is done by the British Geological Survey and has been led by John Mackay. So he produced a paper on this method in 2015. And that again produces forecasts for the next 1 to 3 months across different boreholes in the UK. And it uses the same input data as the grid-to-grid water balance model. It uses rainfall forecasts and mean potential evapotranspiration. And it runs that through the AquaMod groundwater model to produce 1 to 3 month forecasts. So all of these methods were developed kind of in tandem for the first few years of the Hydrological Outlook. And Christelle Prudhomme led a scientific paper that goes over these methods in detail on some of the dissemination techniques as well, that was published in 2017. But why do we bother running 3 different methods, or 4 different methods if you count persistence and analogy separately? Well, there's a lot of difference between forecast skill in the different methods. So they have different skill in different times and in different places. So it's not just that one method is better than the other. They all kind of have their own expertise and brilliance in different places. So for example, persistence and analogy are generally better in the south and east, whereas ensemble stream flow prediction, in the summer, persistence and analogy are better in the summer at 1 to 3 month lead times. Ensemble stream flow prediction is kind of similar. It does also show the best results in the south and east, but it does also have some skill in autumn and winter over the longer lead times. Whereas the gridded flow forecasts that use the meteorological predictions actually have more skill over the autumn and the winter. So you can see we cover some different ground using these different methods, but there's also some gaps in there. There's not much skill anywhere in spring. There's not that much skill in the south and east in the winter, for example. So there's definitely room for improvement. And that's where I'm going next in this talk. So we've been doing various bits of research to develop these methods, and I'll talk to you about a few of those next. So the Hydrological Outlook is generally funded under NERC National Capability funding, and it doesn't get a huge budget. It has a budget to sort of run it operationally, but there's not a much budget for us to develop and improve the system. So what we've managed to do is, because UKCEH and UK research in general is really, it's really important that we focus on drought and flood resilience and seasonal forecasting and the ability to react to these events. We've managed to leverage bits of funding from some of the bigger NERC research programs to contribute to some research that's actually relevant to the Outlook, and we've been able to integrate some of those developments into the Outlook. So a couple of examples of those are the UK Drought and Water Scarcity Programme that ran from 2014 through to 2019. The HydroSOS initiative that's run from 2018 is still going on today. Recently, we've also begun the Canary project that's looking at large-scale atmospheric drivers of drought in the Arctic. And then also our work under NC International, so looking at some of the global, our global research as well. So the first piece of work I wanted to talk to you about was some atmospheric circulation analogues, or historical climate analogues. And this was an improvement in the precipitation forecast input into our hydrological models. So Nikki Stringer has led, from the Met Office, has led a piece of work looking at the link between the North Atlantic Oscillation and precipitation in the UK. And so she's published a paper that improves the meteorological seasonal forecasts in winter, but we've now also applied this same system throughout the whole year as well. And you can see that the NAO is really highly correlated, particularly in the north and west, with rainfall. But that actually translates through to river flow as well. So not only does the North Atlantic Oscillation, which is one of the main drivers of precipitation in the UK, affect the precipitation itself, but you can actually map that straight onto river flow as well. This little plot with the blue triangles on it is a map of the skill of ESP over climatology. So wherever you've got dark blue triangles is where ESP, the ensemble streamflow prediction, is better than climatology. This is where we have good skill in winter in ESP, and where you've got the kind of blank triangles is where really we haven't got any skill. In winter, we can't predict river flows at the moment in the north and west using ESP any better than we can just with a basic climatological forecast. So because that area maps so neatly onto the North Atlantic Oscillation correlation, we're hoping that, and we have found that we can improve our forecast using this method. So the way we do this is Nikki at the Met Office and her team have a look at the Glossy 5 outputs, and they have a look at the mean sea level pressure in the climate runs, the climate forecasts, and we'll have a look at historic examples of observed data and pick out some examples from the historic data where the mean sea level pressure is looking at like a similar pattern. But we have the ability here to jumble up the different months over the season. So we do 1 month forecasts that jumble up different 10-day sequences, and we do 3-month forecasts that jumble up different months. So for example, if we had a June, July, August forecast, we wouldn't have to take June, July, and August from 1 year, from 2013, for example. We can take June from 2013, July from 1989, and then August from 1984. And that makes up a sequence of months that we've never seen before, but that match quite nicely onto the Met Office forecasts. And what we do for each ensemble member, each of the 51 ensemble members that comes out of the Glossy 5 model, is we collect 10 different analogues, climate analogues, and we run those all through the model. So what we do is they will say, well, we think the rainfall situation is similar to this combination of months. We will go through and we will actually extract the observed rainfall that happened in those months and run those through the model. And what this does is it allows us to have spatially disaggregated climate input into our hydrological models to run our forecasts. And the outlook for this, this is the RPSS score, so similar to the last map, where you've got dark blue triangles is where you see an improvement, and this is the improvement over ESP, not over climatology. So we still have the skill down in the south and east for ESP, but there's no real improvement using the historic climate analogues in the south and east, which doesn't really matter because we already have skill for ESP. But there is improvement in the north and west, which is really good. This is an area where we haven't got any skill from our methods so far. So in winter, it's definitely showing promise. And in the other months, it's not quite as good, but it's still not performing really any worse. Just to give you a kind of case study example, in 2015 and 2016, we know we had quite a significant flood event in the UK. This is the ESP forecast as it would have come out in 2015 in December for the next 3 months. These little probability plots you can see show you the likelihood of flows being normal, below normal, or above. The little expected probability looks a bit like this, so you would expect the high and low flows to be quite small. And you can see that this is quite a boring plot. There's not really any signs of anything extreme going on. It's looking quite similar to the expected probability in most of these catchments for the ESP forecast. But when we run the historic climate forecast, you can see there's a real shift to some really significant high flows being predicted here in the north and west and across the southwest as well. So you can see a huge difference in those forecast results. And we know that what actually happened was a really significantly wet event with significant flooding. So had we had these historical climate analogues available at the time, we would have had much more ability to forecast what happened that winter. So that's a really good improvement, and we've implemented that operationally now into the Outlook. We're running that both for, sorry, I'll just go back. We're running that both for the GR6J model, the lumped catchment model, but we're also running that on the water balance grid-to-grid model as well. So we have both the lumped catchment and gridded outputs using this method. Another bit of research that my colleague Wilson has been doing, so this was part of his PhD research, but Wilson's now also working at UKCEH, continuing on research on flood and drought storylines. So these are some examples of some forecasting techniques we could use during an ongoing event. And Wilson published this paper this year on the added value of seasonal hindcasts to create UK hydrological drought storylines. And what he did in this paper was he had a look at the 2022 drought event and what could happen next over the winter period. So using the CS5 hindcast data and using the unseen approach, which had a look at exploring plausible and unprecedented event likelihoods, he had a look at different clusters of the likelihoods of different sea level pressure situations happening and compared them to some of the historic drought events that we have, and then was able to run that through as a basis of, from the 2022 drought, if we had some of those conditions moving forward over winter, what would it look like for river flows in East Anglia, which kind of demonstrated how useful this could be for water resources decision making in the area. And you can see that some of those conditions in clusters 1 and 2 showed the continuation of significant drought events, whereas cluster 3 showed a higher likelihood of some above normal flows kicking in some parts of East Anglia. So it kind of offers an opportunity to have a look at what are the plausible likelihoods of the droughts continuing or terminating. And talking of drought terminations, so I already told you about the 2010 to 2012 drought event that happened, and the really significant transition that we had from drought into flood very, very rapidly. Some work that we've been looking at here, my colleague Rachel Armitage has been looking at this research, is looking at the transitions from drought to flood, and the way what we have this in the historic data, but also looking at this in terms of climate projections. And what she's found in some of her preliminary research, so this is still ongoing research for the Canary project, is that generally, and the historic record, there's a real shift. There's a split between the northeast and the northwest and the southeast in the intensity, with the northwest showing far more abrupt transitions from drought through to flood events, but also that actually in the EFLAG projections, the EFLAG data set that we have, those transitions are likely to be far more frequent after climate change. Another piece of work we've been looking at is model blending and bias correction. So my colleagues Amelia and Barak have been working on this. And as you know, we've got 4 different methods in the UK Hydrological Outlook, and they all have skill in different times in different places. So what we'd really like to do is to be able to blend those methods together quantitatively. At the moment, we're only really doing it qualitatively and explaining using our own expert judgment as to what the likelihoods are of flows being high or low in different parts of the country. But we'd really like to be able to blend these together quantitatively and be able to give a really good, robust map of where things are looking extreme. So we first tested this on some global forecasting data from the Ulysses project. So this is looking at 4 global hydrological models: HTESL, JULES, PCB, and MHM. You can see on the left 4 box plots. And we've just been testing these with the observational, the baseline runs. So we're looking at the Klingupta efficiency and the Nash-Sutcliffe efficiency of how well the models perform over the baseline runs. We have yet to analyse these over hindcast experiments to look at the skill. But what they've started looking at is if you blend the 4 models together just evenly, so if you take an arithmetic mean and you look at that blending them together evenly, you don't get a significant improvement in the Klingupta efficiency. You get an improvement over some of them in terms of Nash-Sutcliffe, but the MHM model is quite good and you don't get really an improvement over that one. So a basic arithmetic mean of blending doesn't really improve your forecast that much, or your baseline run that much. Whereas if you have a look at weighting those models according to their performance over the historic period, over the baseline run, so some models have got better Nash-Sutcliffe's or Klingupta efficiencies over the observational period. And if you weight the ones that are better than the ones that are not so good, accordingly, then as you would expect, you get quite a significant increase in the performance of that blended output. So that little plot in yellow you can see is quite significantly higher in both situations than each individual model run or the arithmetic mean. So what my colleague Barak has been looking at actually very recently, and is hoping to write this up into a paper quite soon, is looking at if you break down your model runs according to the annual seasonal cycle and then into the anomalies away from that, and you have a look at the different models' abilities to simulate those 2 elements, and you weight them according to those 2 elements, then you can actually really improve the skill of the model even further. So this brown bar plot is getting up even higher than the weighted average and each individual model. We're looking at quite good improvements. So those are some different methods of blending different models together that we've been looking at, but we're also looking at bias correction. So models are inherently biased. They have some elements that are lacking or missing in the models, and you can have a look at the flow duration curve and look at if there's a systematic bias in the flow duration curve. And then you can use simple quantile mapping to correct that. And yeah, so we've looked at how this improves the forecasting system. So the continuous rank probability skill score, obviously the higher the better on this. So you can see that there's an improvement. The original ESP runs that blue line, but if you bias correct them, you get an improvement of about 0.1 of a CRPSS, which is a pretty good improvement. But that does diminish over time, so it gets smaller and smaller and becomes reasonably insignificant after about 6 or 7 months. But when you do look at this in terms of the baseline runs, you can see just a huge jump. So these were the pale box plots that we saw on the previous slide, and we have the same again in brighter colors here. And you can see actually that this blend, according to the seasonal cycle and the anomalies, when also bias corrected, you're getting really quite close to scores of 1s for most catchments, which is a near perfect model run. So we're looking at really significant improvements over those catchments. So we're hoping to apply some of those methods into the operational forecast fairly soon. Where, as I say, we haven't tested these on actual hindcast experiments yet, but we're looking at doing that. We've got hold of the hindcast for all of the outlooks methods, and that's going to be our next step, is to analyze how these can improve our forecasts. And this has been published by Mulia, and there's another paper being published by Maliko coming soon as well. So that's just telling you about all of the actual methods that we run. But it's really important as well to talk to you about some of the stakeholder engagement and forecast dissemination. There is no point in having a brilliant forecasting system if you don't disseminate it well and people don't know that it exists and people can't actually use it because it's not communicated effectively. So when we first launched the Hydrological Outlook, we produced the hydrologicaloutlook.net website, and we also produced these PDF documents to show you a summary of the outlook. So this is kind of an expert elicitation, an expert-led description of what's going on over the next 1 to 3 months. We have a map with some blobs on it or some lines on it to show you in a sort of qualitative way what's going on over the next few months. And actually that hasn't changed very much. We still produce much the same PDF documents, very, 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 very similar, with still the same maps. We find this works quite well. But we do also have this PDF document has a lot of background information if people want to dive into it in more detail. But we did find that this is quite a static output and it can be quite complicated. So we've been working to advance on that. And under the UK drought and water scarcity, what we did was we developed our first interactive website. So we produced the UK drought portal, and this showed standardized precipitation precipitation index for different areas and allow people to have a look at the current conditions according to the drought metric of SPI. We also did a lot of consultation under the Endow's engagement programme at the end of the UK drought and water scarcity about what water managers really needed to be able to make their decisions. And one of the key things they highlighted was that they actually really wanted to be able to have a look at what the likelihood of flows falling below certain management thresholds was. So we were able to take the ESP plots, the spaghetti plots that had all of the different ensemble members, and draw lines across these to show different particular management criteria. One of the key points in doing this was actually translating the data away from QMEX and into megalitres per day, because that's the language that water resources managers talk. So yeah, being able to show it in megalitres per day and draw a line across it and have a look at what was the likelihood of flows falling below a certain management threshold. And you get these kind of percentage plots to show you how many ensemble members fall below those thresholds. And that really kind of highlights to them what is the likelihood of them having to take action during a drought event or moving forwards. So we implemented those operationally. Another thing they highlighted was the need for some better soil moisture soil moisture assessments. So using the grid-to-grid model, we now have these soil moisture conditions. It shows you the current conditions, but there's also a few subproducts of this that have a look at what's the estimate of the additional rainfall that's required to overcome dry conditions, for example. And these outputs feed directly into the Environment Agency's Flood Forecasting Centre Flood Outlook. Off the back of the UK Drought portal, we then developed the Water Resources portal. This isn't an outlooks portal, this is just the monitoring side of things. But this was a really groundbreaking website that people really valued, to show you how river flows, soil moisture, groundwater, and precipitation are relative to normal conditions for that time of year. So you can click on any catchment, any gauge point, and you can have a look at the historic data, and then you can have a look at how that compares to what's been going on historically. Shortly after that, we produced the Hydrological Outlooks portal. So using a very similar kind of splash screen, this is looking at the Outlooks data. And as I said, the static PDFs were quite static, and we wanted to be able to show these all in a much more interactive way. So we now have this Outlooks portal that shows you all of the different methods. You can click on the different methods, you can click on the different catchments, you can click on the different gridded squares, and you can see the detail of the forecast in these. And these are presented in different ways. So for example, with the ESP, we have these boxes that show you what's the likelihood of things being normal or high or low, not only as a percentage chance, but also compared to the normal chance. So for example, there's a 1.3 times chance that the outlook for April was going to be high. And you can see these as little bar charts as well. We also present these as box plots, so quite similar to how they are shown in the Water Resources portal. You've got the historic average of highs and lows here in the banding at the background. And then we've got box plots that show you the different ensemble members in the forecast and what the likelihoods are of falling into some extreme conditions. And then we also integrated these threshold plots that the water managers were asking us for. So people can actually go into these graphs and they typing in their own specific thresholds to draw those lines where they want to for any catchment that they want to, and it will draw that line and produce a plot for them. You can also choose historic years, so you can have a look at some analogues and see, well, if we had the rainfall that was going to happen in 1993, how would that move forwards based on current conditions. One of the key components of our outlook is having consistent categories and colours. So the different methods, a lot of the different methods have different categories. So the water balance grid to grid model has 7 categories, whereas ESP has 5. And on the map, we often only show 3 categories, but it's important that we have these consistently. And we've also done some research into this colour scheme as well to make sure that it's really colourblind friendly and intuitive, so people understand that yellows and orange and oranges and reds tend to be low and blues tend to be high. And you'll notice that the normal bracket is quite a big bracket. It's 28 to 72%. This equates to about 2 standard deviations away from the mean. So yeah, this is looking at they're not even categories because they're related to the distribution of the curve, but the normal category is 28 to 72%, and then the above normals are aggregated accordingly into more extreme blocks. So that's what we've been doing in the UK. I also wanted to talk to you about some of our international research just quickly. And one of the things we've been looking at with the World Meteorological Organization is HydroSOS, and this is the Global Hydrological Status and Outlooks System. And this is basically trying to produce for the whole world. What we have in the UK is very similar to what we have in our hydrological summary, our current status assessments, and our hydrological outlook. So we're trying to kind of integrate those 2 products in as coherent a way as possible. So HydroSOS is aiming to provide an overview of the current hydrological status, an appraisal of where that status is significantly different from normal, and an assessment of whether that's likely to get better or worse over the coming weeks and months. And doesn't that already exist? Well, there are lots of examples, as we have in the UK. There's lots of national examples of products that look at hydrological status and that do forecasts. There's also global instances, so the GLOFASS system and the SMHI Worldwide HYPE system provide forecasts and status assessments for the whole world. But they're all slightly different. They're all put in different websites. They all use different colours. They all use different spatial aggregations, and they all use different categorization systems. So what HydroSOS is really trying to do is to bring these together in a coherent framework so that we can look at them side by side and we can really get an understanding of what's going on globally, not only from global models, but also using local information as well. So any existing forecasting or status assessment systems can be just post-processed. So we're not asking people to change their methods at all, but just post-processing the information so that it's in a consistent categorization that we can compare like for like across the world. And the way we're doing that is through liaison with lots of different partners around the world and different hydrological advisors in different regions. But we're also providing some tools. So we have an R script that will calculate hydrological status for any input, whether that's groundwater input or river flow input for a gauge point. We have this code in R that will do this calculation for you. It's also been translated into Python, and there's an Excel spreadsheet as well that does the same. We haven't got as far yet as to produce basic forecasting scripts, but we're hoping soon to be able to have some scripts that will provide the method of doing some persistence and analogues forecasts or some ESP forecasts for anywhere in the world. And we've done some engagement. So we had some partners over from Ghana to UKCEH to have a look at producing some ESP forecasts using some of their data. And that was really successful. We were able to do some hindcasts at least, because their data didn't run quite up to current times, but we used some satellite rainfall data and we were able to run some examples of forecasts that they could then have a look at, trying to promote that system in Ghana. We also had a workshop in Nairobi, having a look at the Lake Victoria Basin and looking at status assessments for different gauge points in the Lake Victoria Basin, and also looking at status of aerial average rainfall as well, and did a little demonstration of how that could work in the Lake Victoria Basin. And we're engaging with those partners continually to try and get that operationally moving. On the global scale, we're also having a look at translating some of the global systems into HydroSOS. So this is an old example, I'm afraid, because we're still currently working on current operationalization, but this is just a prototype of what we could do with the SMHI data. So we had a look at translating that into hydrosheds basins, just to provide a consistent spatial aggregation and translating all of that into the same colors so that you could click on those polygons and get a forecast moving forwards and a status assessment as well. And we're also integrating some drought indices as well. So working with the Outlast program, we're looking at drought indicators as well, and importing those. So this is a standardized precipitation index for the whole world. And again, we're looking at getting that data in operationally. So yeah, that's a summary of what we've been doing and what have been our key lessons. It's been a lot of research over the past few years. It's been a huge amount of collaboration with different users. And we've definitely made a lot of progress in different areas and fed that into both status assessments and hydrological forecasting, as well as developing lots of our methods. The key lessons I think we've learned is that it's really important to assess your skill. There's no point in having a forecasting system if you don't know how good it is and you can't communicate how good it is. So it took us quite a few years to assess the skill of our system, and now we have. That showed us really the areas where we needed to improve the system so that we could then have a look at exploring new methods. And there's huge wealth of different methods out there, and we've as I say, I've mentioned a few of the methods that we've been looking at. Some have been more successful than others, and so yeah, we're trying to implement certain things operationally now. And you need to engage your audiences. So as I've said, there's no point in producing a forecast if you can't make it useful to people, and part of that is being able to communicate it not only effectively but efficiently. A lot of forecasting systems are extremely complicated. Ours is currently extremely complicated, which is why we're looking at trying to blend it together more quantitatively to make a more simplified result. So that's all I had to talk to you today. Thank you for inviting me, and I'm happy to take questions in the last few minutes that we have on this call.